into this this new lab. Mark will kind of lead that on dynamic linear models.
Can you share your screen on Zoom? So it's
oh, yeah. I think this will be the last lab as well. This DLM one.
I think we have one more, but the next one is methods.
Okay, yeah. So no, there won't be any other class projects, or there won't be any other labs to work on other than your paper efforts. Okay, we should talk with Mark, because I think the week that you were gone, he and I were talking about it, and if we pushed it back, we'll talk about it later. Okay. Sorry. See, no, oh no, what's going on? Oh, you know what? It's the Zoom thing. If I share my screen on Zoom, then I can't do the full screen. It's fine, but that's the problem, because I was just able to do that.
Okay. Can you make this full screen in Zoom?
View full screen. And if I go back to, oops, make that smaller and come back over here, that, and go full screen. There we go. Okay. Never mind. Operator error. Today, so we talked a lot about univariate GAMS and time series on Tuesday. We're going to take those same ideas with the univariate models. I'm going to extend them to the multivariate case, just as we did with DFAs and the Mars type models, and also talk about some of the finer detailed questions that came up on Tuesday, just for general clarification. I think there's two really great resources that I'll kind of base all of these slides off of. Again, this is new material, largely because this this field of kind of multivariate GAMS is evolving rapidly, and there have been some really good papers coming out in the last few years. This first reference by Eric Peterson and colleagues is in Peer J. And it's kind of an introduction for hierarchical GAMS in fisheries and ecology. I think that I was thinking about this. I think that since 2019, for all of the student committees that I've been on, this is the only paper that I've always recommended for everybody's qualifying exam, because it's so accessible and really easy to see. They have really great examples. The paper's really accessible. And so for an introduction to hierarchical GAMS, this is the best thing out there. And it has a lot of applications beyond just GAMS. So I really love that paper. The other one is this paper that came out in Methods of Ecology Evolution by Nick Clark. And so this is all of the material that's sort of new today. And so what Nick has done is he's built this R package called MVGAM that we'll talk about today. And what's cool is a lot of his vignettes and examples for that package are largely based on kind of the Mars examples and book that Eli and Mark and I have put together. And so I think it's really neat to see kind of the same time series, whether we're talking about seals or the Lake Washington data set, analyzed again in this new framework with multivariate GAMS. So both of those are definitely worth checking out. Multivariate models in MGCV. So MGCV is the univariate GAM package we talked about, super flexible. We can also fit these multivariate models in MGCV, and so I'll talk about that in the context of kind of following the same thread as Eric Peterson's paper. Just like with all the other multivariate time series data sets we're working with in this class, we often have multiple related response variables or multiple replicate observations of the same response. So this would be multiple fish counts at different sites, or maybe different tree species at different locations. And the goal here is to model the shared as well as the individual site-specific responses while trying to account for all of the different complicated correlations that might arise. And so if we have this data with multiple time series, multiple sites, or species, there's so many ways we could think about modeling this kind of variation. In the context of Mars, we talked about modeling each different site as having its own trend or own kind of latent state. That's one option. We could have a shared trend. We can have shared, the shared linear trends, that the U parameters can be shared or different across sites. So a very flexible way to think about how to let these things be shared. We could extend this further, thinking about moving beyond out of the Mars framework into working with linear mixed effects models. And I think in that context, we could think about the sites or the years or even these site year interactions as being random effects. The difference here is that when we have the site year interactions as being random effects, we no longer really care about the structure. We're saying that the variability between site and time is just random, and so there's no consistent bias where one particular site has lower than average catchability. It's just random. And then last point here, another way to deal with this is what's called factor smooths, and this is something that's very specific to this class of models with GAMS. Okay, so what is a factor smooth? Factor smooths are a way to create smooth terms where we have a continuous response and we have some categorical variable. So this categorical variable might be species or site, etc., month. And we want to let that categorical variable interact with our predictor to have this smooth relationship that varies. And so we can let that smooth, vary in different ways across different levels of a factor. And so in some sites, you might have higher than average catchability and an increasing relationship with temperature, whereas in other sites, you might have no relationship with temperature or even a decreasing relationship. So we're allowing that wiggliness to vary across locations. Okay, so how do we implement these in MGCV? We used on Tuesday, we used this S notation to denote kind of the smooth that we were working with. And we would say we have our predictor variable. So this could be time, and by is our factor variable. When this by is a factor, then a separate smooth is estimated for each level of that variable. And so if this is site, then we're going to have separate smooths estimated for each site. Okay, so this is all super complicated because we talked about a number of different ways that this by thing can be set up on Tuesday, and I just want to make sure that these are all crystal clear because it's easy to make mistakes, and it's really important, I think, to understand what's going on. And so I probably should have had these slides included in the material on Tuesday, but these are three different ways that we can use that by term. All right, and so in the first one, this example would be this S time by equals X, where X is a continuous covariate. That's basically what we were talking about on Tuesday, where I was trying to show or kind of work towards examples where we would have something akin to a DLM, where our covariate effect was varying through time. And so in that case, we were working with personal savings rate as a function of unemployment, and we were putting the covariate was going over here, not time. And so we were basically setting it up that way to have a DLM. The second approach, so we have this variable called location maybe in this data set. And so we could set up another smooth where we specify, I guess, backing up, this is just specifying the spline here, but this is totally optional. We could take this out and the same thing would be true. So that's not going to, changing that BS argument is not going to change anything there. In the second argument, we're not specifying any kind of BS argument, but the location here is a factor. So that's a second way to set this up. And the third way is to set that up with the BS argument being FS for factor smooth. Okay, so in both of these examples 2 and 3, location is a factor, and we're going to talk through what that actually means. So in the first example, this is going back to what we talked about Tuesday, right? We have a spline over time. We want to create something akin to a DLM where our covariate effect is varying through time. So we say that we're creating that smooth over time by the covariate, and essentially what that's doing is we have this smooth function of time that the GAMS is generating, and we scale that or multiply that by the covariate. And so X is a time series, and this smooth thing, this f of time, is a smooth time series. And so we're just multiplying one time series by another, and what we end up with is also a time series, so that it's also going to be smooth. So that's how we set up the time varying covariate. We can extend that then so that we're only talking about the S smooth, this univariate smooth in this class, but I think we could also expand tensor product smooths or interactions with the TE and TI terms. And that creates similar effects, but it makes the relationship between X and F of time nonlinear. So that becomes more complicated. So that's essentially what the examples we talked about on Tuesday are doing. Now, what if that by thing is a factor? And so this example is the second example on our list. If we have a smooth over time and say by equals location, and we don't specify the basis to be a factor smooth, what it's doing here is it's really going to confuse the MGCV package. And so really, this is the wrong way to do this. Don't do this. What's happening here is that the MGCV package will try to create smooths that vary for each location, a separate smooth over time, and each smooth is going to have a different penalty. So it'll have a different amount of wiggliness, and it will be confused about whether location is really a factor, because we didn't specify a factor smooth, and so it's going to be confused about whether location is a factor or whether it should try to take it from whatever the factor is that's passed in and strip it to a numeric variable instead. So MGCB gets confused by this and will give you something that's different from what you're actually intending to do. Okay, this is really here what we want to do. And so in this case, the same thing. We say we have our location variable as a factor, and so here we say the factor smooth is the basis. This is exactly the right syntax. So what this does is it creates unique smooths for each of the locations or each of the levels of the location variable. And by default, the penalty or the wiggliness is going to be the same for all levels of the factor. And so I think in most of the GAM applications, this makes a lot of sense. If you had maybe time series of different species or maybe different responses or species that had different amounts of process error, and so they were changing on different time scales. One of them was changing very smoothly, and the other was changing, really, really rapidly. The time step to time step variability was high. Then in that case, I think those would really warrant different smoothness or penalty terms. But in the case of if all the responses going into the model are the same species or the same kind of survey, it probably makes sense to let that penalty be shared. Okay, so let's talk through three of the examples from the Peterson et al. Paper. We're basically going to apply to the Harbor Seal data set. This code chunk is just going to take our Harbor Seal data. We're going to take not just the Puget Sound data, but all of the different Harbor Seal time series that we have coast-wide. There's 12 of them, and create a factor for location. So we have this location, relevant for each series. For comparison, we'll kind of pick three models here. We'll have model G, we'll call it, is going to be using a global smooth. And so you can think about this in the context of the Mars models. This is essentially a single trend or single smooth relationship over time, and all populations share the same trend. Okay? Model 2 is what's called model GS. And so in this case, we're going to have that same kind of global trend shared across all populations. But we're also going to let each population have a slight deviation from that. And it's going to get its own extra smooth term. But all of those smooths are going to have the same wiggliness. Then finally, we can talk about what happens if we were to take model GS and basically remove the global smooth. So model S, each of these time series are essentially having independent smooth terms without a common trend. Okay, so this is the first model. This is model G, and kind of using the same syntax as the Peterson et al. Paper. We're going to specify a smooth over a year here. Because we don't care about differences between locations, there's no factor smooths here. We're going to set the number of basis functions to be 8. That's somewhat arbitrary, but is enough to kind of capture the wiggliness that we need. And otherwise, this is a very simple GAM. Here are what the fits look like. So again, 12 time series. The blue line represents the model predictions. The red line represents the dots. And I think two things are, if we squint, it seems like maybe on average the trends are about the same across all of these sites. There's some, like maybe the San Juan Islands that are increasing faster than others. So that's one thing. Another thing, though, is that the model is really missing a lot of these populations. So if we look at something like the Georgia Strait time series, really underestimating, and in some others, for example, the Hood Canal, really overestimating. And the reason here is this is sort of like a Mars model where we set that A vector that scales all of our predictions. That A vector is basically 0. And so we're not accounting for the fact that some of these sites have different abundances than others. And so what I'm going to do is take that model G, and we're just going to add that scaling, that extra scaling, to allow each of these populations to essentially have a different level. Okay. The way that we're going to do that is by implementing. There's several ways to do this. You could include location as a fixed effect in these GAMs, and that would be totally fine. I'm going to include it as a random effect, just because, no particular reason. The way that we do that with MGCV is we have our location variable or our grouping variable. We specify RE for random effect for the basis, and because of the random effect basis, we specify the number of levels of that variable. So in this case, we have 12 locations, 12 levels. So what this is going to do is still fit the same model G with the same global trend, but it's going to estimate these different intercepts for each of those different time series. So here's what happens when we do that. This looks a lot better. Something like Georgia Strait that was that was really underestimated before. Everything is shifted up here. Same with Hood Canal. Everything got shifted down. So in general, this looks like it's a pretty good fit to the data. Okay, so that model, the first model was super simple, no factor smooths. In the second model, model GS, we'll take that same global smooth, single smooth, and we're also going to add these time series specific smooth effects. And we're doing that by saying with the second line here, where we're saying that the basis here is going to be factor smooth. We're adding this smooth over year by location, which is the factor. We're going to keep those random effects in there just as we did before. Okay, so this is I guess harder to see probably on here than on my screen, but the original dark blue lines were the original fits. That was just the model G. These lighter blue lines are model GS predictions. And so for some of these populations, Puget Sound, for example, there's no distinction. They're right on top of each other. Olympic Peninsula, Eastern Bay is the same. But some of these, I think, for example, if you look in the top left, the Channel Islands one,
you can see the effect of the wiggliness, or the time series specific smooth, where before, the model predicts with the global smooth, the model predicts that this population is increasing because this trend is shared across every other time series up here. So even though there's no data, it's borrowing information from the other locations to inform that smooth. When we relax that assumption, though, and include time series specific smooth effects, what's happening is the model notices that there seems to be actually a decline here, which is kind of awkward at the beginning of the time series. And so it's really flexible, and it allows for a better fit to the data. Okay. So third model, so that was model GS, was the last one, where we had the global smooth and these time series specific smooths. We're going to drop out that global smooth now and just we still have this factor smooth where we're smoothing over location, still have the random effects. And we can see what's happening in the bright green lines, which are on top. And so in general, we get very similar predictions as with the previous two models. We can see that, in the top left in the Channel Islands, this model S is doing the same thing as model GS, where it's saying that the population is declining. But we can also see that when we don't have data, the model really struggles. And so an example of that would be with this Hood Canal population, we only have, there's a huge data gap here. So the model can fit the time series here, but it's pretty wiggly, and it also has a really probably unrealistic rate of increase towards the end of it. So that model S represents the model with no global shared trend. Okay. Unfortunately, this model table did not print, but I wanted to kind of quickly summarize using AIC what the relative support for these various models was. And when you look at the various support across these three models, the last one, this model S, does the best. I think that in reality, if you were interested in the kind of estimating the global trend in your model, or maybe interested in other metrics beyond just AIC, I think that would lead you down a path of kind of selecting model GS. But in general, these models fit the data really well, give very similar answers. But the smooths are probably, depending on your question, that would lead you down the road of picking different smooth terms. So those factor smooths that we talked about, we're adding this flexibility. It's really similar to Mars models in that we can have a shared single trend. We can have kind of time series specific trends, and we can specify, in these examples in model G and GS and model S, we're allowing the smoothness to be the same across all of those time series. If you look at the Peterson et al. Paper, there's examples too of extending those models to let the wiggliness of all of those terms, the factor smooths, for example, vary by time series, or by the level of that grouping variable. Yes, so just to wrap up the MGCV stuff, these models are super flexible. There's other approaches for mixed models and smooths using GAM, the GAMM package, and similar approaches for mixed models that are kind of beyond the scope of this class. But MGCV, super powerful.
Eric,
yeah.
Can I ask a question before you move on to GAMS? So, one of the things with Mars models is we get out this matrix of the variance covariance. It kind of tell us about how these, how our populations are related, whether they are covariing. Yeah, like if the wiggles from step to step are related with each other. And does this one have that, or is it more just that the wiggliness can be related? Like, I mean, from like in the Mars, you can say that your time step, like how much you go up and down across each time step can be related to each other.
Yeah, no, that's a really good question. I mean, one way that you could do this, and this might be circular, but you could take the predictions from each of these and calculate the difference between time steps and see if those differences were correlated. But these are very smooth things that are going to be different from the kind of the random walk is going to be more variable. So not exactly the same. I think though, in general, no, you can't get the same kind of thing out of here. It's mostly evaluating whether the populations share a smooth trend or not. I will say too, a limitation of this approach is that these hierarchical GAMS are really powerful. We talked about like this model GS that allows for a global smooth and then time series specific smooths. And with that kind of model, you can think about it as something like a DF. Like with DFA, we have one shared trend, and we have different time series that are loading on that trend. But with a multivariate GAM, maybe this is sort of similar, but we can't fit a model that has 2 or 3 latent trends the way we can with the DFA. And so we can't fit, if these populations were grouped or there was maybe 2 species, we wouldn't be able to easily fit a model with MGCV where we could have species-specific trends and time series-specific deviations on top of that. Okay, so that was everything with GAMS, and then we're going to be now transitioning one step further into these DGAMs, and so DGAMs are in this. DGAMs stand for dynamic GAMs, and they are dynamic in the sense that all of the models that we've worked with in this class so far, the Mars models, the DFAs, any of these state space models that have the process model that's the random walk, they can be all kind of collapsed into this family of models that are called dynamic. And so, so these dynamic GAMs are going to be kind of a hybrid between the GAMs that we've talked about plus the models that we've learned about to date in this class. And so the state space models plus a GAM gives us a DGAM. They're all implemented in the MVGAM package, which is, it's powerful. It's really similar to BRMS, which for anybody that's used that, in that it all has kind of the Stan programming language as a backend. So the estimation is all Bayesian. And because of that, the estimation ends up being quite a bit slower than what we get with Mars or MGCV or these maximum likelihood packages. Right, so DGAMs, they are particularly useful when our time series our data have a time series aspect. GAMs and MGCV are not exactly meant for time series, and I showed you the examples that I showed you on Tuesday and today are kind of hacks to make it work. Because the DGAMs have this dynamic component that represents the state space random walks that we've talked about. They're much more suitable for fitting time series data and doing forecasts with that data. All right, so GAMs are, like we've talked about on Tuesday, GAMs are great, and like random walks, the further we get in the future in terms of our forecasts, the wider our prediction envelopes get, and uncertainty really balloons. Random walks, AR1 processes all do this, and so DGAMs are trying to kind of split the middle and include a GAM that fits the training data reasonably well, and combining that with a random walk that can be used for forecasting. And so just to illustrate some of the GAM forecast challenges, these are not specific to GAMs either. These are the same kinds of issues that come up with random walks. The blue dots here represent kind of some simulated data that I simulated with a sine function. And if you squint, you can kind of see that pattern, but it's a little bit hard to see. This model here is fit with a very simple smooth over time, and it has 12 basis functions. So K is 12. What we see here is that the red line, data up to the red line represents the training, the fit to the training data, and the gray bar over here represents our forecast. So when K is 12, we get, this is just a terrible, awful fit to these data. We're basically drawing a straight line through this shotgun blast. And so that happens, but we also get really good predictive uncertainty, right? Our forecasts in the future are really low because we're fitting our data so poorly. So what happens? So here's the other side of the spectrum. If we just ratchet up the number of basis functions that we're including from 12 to 50, all of a sudden we can fit that, the wiggliness in our training data is fit perfectly. So we fit the training data perfectly, and then we try to forecast from that, and everything just blows up. So we really want to try to find some kind of middle ground between those where we can have some explanatory power for this part of the data, but also be able to produce reasonable forecasts. Okay, so I talked about this on Tuesday. This should be kind of a review. The way that we set up the GAM is kind of just this typical notation that you'll see in papers and textbooks, where we have some response on the left. We have a global intercept with the beta naught, and then we are just going to be adding some number of univariate smooth terms where each of the i's represents a different covariate that we're including. This might be 1, this might be 10, and we have predictions for each time step based on that smooth. We also talked about a little bit about this is so weird. Oh, you know what? There's a wrong symbol here. There should be a negative, not an equal sign. But this G inverse is the inverse link function, so that one of the benefits I talked about on Tuesday with the GAMS is that, like a GLM, we're not constrained to working with normally distributed responses. So all of the stuff on the last slide, our predictions, are in this inverse link function, because if we're working with a Poisson model or a log normal response, we're going to be trying to estimate all of these parameters and these smooths in log space. And so in that context, the G inverse, we would be exponentiating to get back to normal space. Okay, so because all the examples that I'll talk about today are going to be kind of a normal or Gaussian response, we can just ignore this G inverse thing. It's going to be, because with a normal model, our responses, or the inverse link or the log link, the link is going to be identity. So we can pretend that doesn't exist. Just focus on the stuff in parentheses. So this is going to go, we're going to go from a GAM model to a DGAM model by adding this Z term here. And so Z represents the random walk. And so this first part represents kind of the smooths. We have the global intercept again, and then this represents this dynamic random walk with Z sub t. So Z sub t can be modeled, in its simplest form, can be modeled just as a random walk. It can be also modeled as an autoregressive process. In this case, we've got Z sub t is modeled as a function of these two psi terms, and that allows this flexible random walk. It also introduces a process error variance. And so, getting back to Eli's question about does a GAM have something that's akin to a Mars type model where we might be able to take this covariance matrix and evaluate the correlation among time series? The regular GAM approach doesn't, but we are going to be potentially estimating these variances now for some number of processes, ranging from 1 to the number of time series we have, just with the Mars model. So we could potentially take that covariance matrix and then infer something about structure from that. So these Z's become very, very flexible. we can, in the DGAM package, so in the Mars package, we are generally working with the processes being random walks. And in the DGAM package, we can extend that so that we're including, I guess in the Mars package, we are also including autoregressive random walks because we have this B term. So we have first order autoregressive random walks and random walks. In the DGAM, or in the DGAM context, we can make this latent process, this Z vector, be an autoregressive process up to order 3. And it can also include a moving average component, again, up to order 3. So pretty flexible in terms of the AR and the MA parts of this. Further, the last complication is that when we have more than one time series, we might be interested in estimating, some number of processes that's smaller than the number of time series that we have. So this is just a DFA in the context of the DGAM world. So in this case, this would represent some, the Z's here would represent some underlying processes. The thetas represent the loadings on those processes. And it's basically combining then a bunch of squiggly predictions from these smooths with the DFA part for that latent trend estimation. Okay, so then I think we're going to get away from the math, talk a little bit about some examples for what this looks like and how easy it is to use the MVGAM package. It supports, so it's, as I said, this is all Bayesian. I think that these models that I'll talk about realistically take probably 3 to 4 minutes to run for each of them. We can do univariate, multivariate smoothing, or univariate, multivariate models. And it's really easy to get all the output into the tidyverse. So all the models that we fit with GAMS, with MGCV, we can fit with MVGAM. In this first example, I showed that example where I simulated some data, and when we ratchet K, or the basis functions, up to 50, our uncertainty just really balloons. And this is the exact same model with the exact same predictions fit with MVGAM, and we get the exact same predictions because there's nothing special about this model other than it's being done now in the Bayesian context. But we're getting the exact same predictions as we would with MGCV. Okay, harbor seal example with MGCV. So I started the lecture today talking about the harbor seal example and how we might use these factor smooths to let each location have a specific smooth in addition to a global smooth. We can fit the same model now. Basically, you can take the exact same code chunk that you would use for fitting the GAM and just paste it into the MVGAM function, and it does the exact same thing. So we can pull out all of the various quantities of interest, including this is the kind of the overall trend for that. This is the global or shared trend for that model. It's, if we were to plot this on top of the predictions coming out of MGCV, again, they'd be totally identical. Okay. Next, I wanted to create kind of a more realistic example with some new data. And so this is coming from a coastal upwelling data set. This is generated from Mike Jaycox and some colleagues of ours, of Eli and mine, at the Southwest Fishery Science Center. Mike has done a lot of work with upwelling indices, which is a big source of nutrients on the west coast of the US. And so Mike has he's kind of updated the indices of upwelling that have been used historically. And he has these two cutely named indices called Cutie and Beauty. And so they represent slightly different things. Cutie is an estimate of vertical transport at different locations along the coast. And Beauty estimates of nitrate flux. So all the examples that I'll talk about today are based on Cutie. The data are pretty high resolution. So these are monthly time steps. I think that they go back to 1980. They are collected or estimated at 1 degree latitude resolution. So that's that's a lot of points. I think just for dimensionality's sake, I cut this in half. And so starting at latitude 31, I'm going to be using the predictions or the time series from every other cell, so not continuous. And this data did not print, unfortunately. I'll fix that later. But essentially, it's a data set now that has, for each month-year combination, it has predictions at each of those locations, by latitude. So latitude is kind of our grouping variable. We've got a time series of 500 data points, I think, per location. And as I said, BRM, like the whole BRMS and MVGAM package are really great, but because Stan is being used as the backend, it takes a while. And I think if you wanted to fit these models for the full data set, it would probably take several hours. For the context of just like generating the slides for this class, I restricted this analysis or the fitting to just using data from 2023 to 2024 as the training set. And there's three or four observations in 2025 that we'll use for testing. So each of these facets represents a different latitude going south to north. And what you can see is that the effect of upwelling is, as measured with QD, is variable in a couple different ways. It varies a little bit by season, and so not all these locations seem to have the same pattern. There also seem to be different magnitudes of change by different regions, and so especially in the middle regions here, latitude say 39 to 43, we get much bigger fluctuations than we do especially in the south. We go down to like latitude 31 or 33. The fluctuations are much smaller. And in general, I think that there's also some evidence of a shared pattern or trends in that we see kind of these seasonal effects with peaks and valleys occurring kind of during similar months for all of the time series, even though some of these are really, really dampened. Okay, so there's 3 or 4 of these various models that I wanted to kind of talk about and discuss, apply to these data. We'll look about some of the predictions for these and kind of see that they're generally pretty similar. They're kind of trying to do the exact same thing. So this first model, we won't include any latent trends. So there's nothing special about this model that would make us want to go down the road of using MVGAM. We could fit the exact same model using MGCV. We'll include a smooth over time, which is just going to be essentially the month from the beginning of the time series as a numeric variable. We'll include factor smooths, letting each of our latitudinal locations is going to have a specific smooth. We're going to include this random effect for latitude, which lets each of our different grid cells have a slightly different intercept. So if we go back to what that data looked like, that was another thing where some of these, while these are I think generally standardized to have mean 0 across all latitudes, it seems like some of them, this is like latitude 35 is a good example. The mean of this time series is definitely not 0. So we need to allow for some kind of shift up and down on the y-axis in terms of the intercept. And we'll do that with these random effects. Okay, and the last piece here, again, is something that we could also plug into MGCV. We're going to include one of these cyclic splines over a month to account for our seasonality. So the seasonality here is just trying to account for the fact that the first year of data has this peak in the summer, as does the second year of data. And that seasonality, if it's shared across years, we're going to try to estimate a single kind of seasonal shared effect across all these years and all these locations. Yeah, so I think that's it. We're gonna that's essentially this first model, and we can pull everything out of it as before. One of the interesting things I wanted to show was kind of this month effect, and I should remake this. I'll remake this slide so it doesn't get squished. But the month effect is interesting because it definitely shows the effect of this nonlinearity. It's not a very smooth curve in that we couldn't really approximate this well if we included a second order or third order polynomial. It seems like there is some support for including this variation by month. So we're including 12 knots essentially, and estimating a much smoother trend over seasons. So this is the seasonal component of that model. If we look at the kind of what's going on with our time effect, this is the smooth over the entire time series. And we can see that this is also maybe trying to account for some of that seasonality because it's got peaks at about the same times and troughs at about the same times. This is the smooth. Yeah, it's kind of agnostic with respect to year because it's months since the start of the time series. Another way to set this up would have been to include, if we had more than 2 years of data in our training set, we could have also included a smooth over multiple years and then had the year effect and the month effect be separate. Okay, so how does this look in terms of our predictions? Again, each facet is a different location. The points here are the actual observations, and the solid black lines are predictions. So what we see is, in general, things are looking, generally really good. Where the model seems to maybe struggle is in some of these middle locations. Say latitude 41 definitely underestimates these 3 points. 39, the same thing. 43, the same thing. So the forecasts maybe are not great, but overall fit to the training data set seems to be actually quite good. We can look at our, some of the residuals that are coming out of the package. QQ plot maybe doesn't look great for some of these values at the lower end, so the smaller observations. And then the other thing is in terms of the autocorrelation of the residuals, there seems to be maybe some problematic positive autocorrelation. But in general, the model is doing pretty okay. Okay, so taking our GAM that we had before, this is like these four lines. I'll just call the GAM part of the model. We can add the trend part just with a trend model argument. And again, this is just going to be a simple random walk. You can make this be higher order autoregressive processes, including moving average processes, Gaussian processes, et cetera. So this is the only thing, this line is the only thing that I'm adding here. And we can see that the ACF seems to be a little bit better when we include that trend. So now the ACF is centered on 0. And the QQ plot looks a lot better. So including the trend included a little bit of extra flexibility that I think really helped fit those lower values. Even the upper values here with the QQ plot seem to be doing a little bit better. So adding a trend seems to increase the flexibility beyond just what an MGCV or what a GAM can do. So we can pull out the various things that are estimated in the model. Again, this is the time component representing the months since the start of the time series. Again, we have the same kind of peaks and troughs representing the seasonal cycle. Nothing really surprising. And what's interesting here is that if we pull out the trend, so we have two pieces here that are, I think, trying to do something that is very similar. We have the smooth coming from the GAM part of the model that is the smooth over all months since the start of the time series, and we see the peaks and valleys. And then we include this trend, which is also very flexible. The trend, again, is just a random walk. And In this case, the trend seems to have a little bit of ups and downs, but in general is pretty flat. And the variance, is, as we get with the random walk, the variance is increasing. So I think that these two things are both really flexible ways to do the exact same thing. And that might be the kind of the reason why the trend here doesn't seem to be very different from zero. And the smooth part, this first part, is really sucking up a lot of the variability that the trend might otherwise try to explain. Okay, so when we include that trend, what happens to our predictions? Well, it seems like if we look at the fits to the training data, our training data predictions seem to actually be a little bit worse. So we seem to be kind of missing, some of these peaks in especially middle latitudes, 39, 41, 43, et cetera. The peaks and valleys seem to be really missed with the black line when we include that trend, as before when we just had the GAMS smooth components, things were looking a little bit better. So as I said, I think that maybe one way to think about this is that this trend model might be trying to fight with the smooth term to explain that variability. So what we're going to do instead is drop out the smooths. And so in this case, we'll drop out, this text is wrong. Instead of dropping out the main smooth, we're going to include the main smooth, and we're going to drop out the factor specific or time series specific smooths coming from the factor smooths, and include the trend model again. We'll also try to change the trend model to an AR1 model instead of just the random walk. So when we include that trend as the random walk and don't include the factor smooths, this does a little bit better. It still is not as great as what was happening when we just had the MGCB or GAM components. We see that these valleys and these peaks, especially again in middle latitudes, seem to be problematic. So it's really those extremes that the model is really struggling with. Okay, the last model that we'll talk about then is going to be an example of bringing in these factors. And so the factor approach, as I said, we have, we can set up these DGAMs to have a smooth component coming from what's the GAM part of the model. And then we can also include essentially a DFA component that represents these latent variables. So this would be useful if you thought that instead of estimating a single underlying trend for each of our different 9 locations, that because the variable of interest is the same across all locations, we might be able to reduce the dimensionality and estimate a much smaller number of latent trends, and then estimate the factor loadings for each of those variables on each of those trends. In this case, we do this by saying use LV stands for use latent variable. That's basically turning on and off the DFA component. And then the number of latent variable components. In this case, I'm going to set it to 2, just totally arbitrary, but just for this example. So we'll estimate 2 latent factors. Everything else in the model is going to stay the same. We'll keep the trend model also as AR1. Okay, so this is the result from coming out of the model. We have these 2 factors that are estimated. Again, like with DFA, the actual, if we were to rerun this model because of label switching, every time we run the model, the actual numbers corresponding to these trends might change. So the next time we ran the model, it might say that factor 1 was actually this pattern and factor 2 was that pattern. It's not really important. What is important here is that there's two kind of different patterns that I think can kind of be described as a high frequency signal described by factor 1 and kind of a smoother, lower frequency signal described by factor 2. So we have those 2 components that we can pull out. Again, sorry, this plot is squished. I'll fix the slide. And so what did the loadings look like? Well, unfortunately, this table also did not print. I'll fix this later. So I'll describe it. But basically, we have these two factors, and because we have this strong latitudinal gradient, back here, we have 9 sites, strong latitudinal gradient from 31 latitude to 47. And what we end up getting is also probably not unexpected, a gradient in factor loadings in terms of how each of these locations loads onto those variables that we see. So the way it works is that the really smooth the really smooth factor described by factor 2 is kind of loads heavily on these higher latitude locations. So say location 39 north, and the locations in the south, 31, 33, 35, et cetera, those are have high loadings on the high frequency change. So it's harder to see that from these kinds of plots, but that's basically what the table suggests. Yeah.
Can you go back to the slide when you showed the latest trends?
Trends, yeah.
I'm just very curious why factor 2 has very isometrical intervals at some points of the time series.
Yeah, good question. It could be because I ran it for the total chain length was like 1,000. So I don't know. Maybe I need to make sure it's actually converging. And then finally, yeah, so these are predictions from the factor models. Again, these are also seem to be really struggling. So instead of estimating 9 trends for each of the different locations, we're estimating 2 trends here. Again, we really are basically drawing a straight line, it seems like, through some of these data and not really fitting the peaks and the valleys very well. So the factor model alone doesn't seem to be really flexible enough to be able to fit these time series. Okay, so in summary, I think like the multivariate models I showed in MGCV are a really flexible and useful approach to modeling multiple time series. The factor smooths, when you specify them correctly, provide a really clear relationship, I think, that lets you look at how the smooths are changing across different levels of your factor. The MVGAM package that I just talked about extends that approach with dynamic components, letting you include all kinds of things. Complicated latent random walks and dynamic factor analysis models. And these DGAMs can be even further extended to include all kinds of complicated correlation structures. So very, very flexible. And then also, just as kind of a comparison, word of caution, I think that all the approaches that we've seen in this class and all of the GAMS stuff that I talked about have really trade-offs between how well we can fit our data and how well we can make predictions in the future. So the GAM and forecast error example is largely dependent on the number of basis functions. As we increase that and increase the wiggliness of our fits to the training data, we really the trade-off there is that our uncertainty in terms of predictions on future data really blows up. And so similarly with Mars and the DFA, the predictions and the forecast error really depends on the numbers of factors and whether they're shared or not, how they're modeled, and all of those choices. So ultimately, your choices are going to obviously depend how well your forecast error, et cetera, does. Okay, well, with that, I think that is all the material I have. I think we can jump into lab unless anybody has questions. Actually, we should take a 5 or 10 minute break. Yeah, Eli.
Yeah, I have a question before you move on.
Sure.
So when you set it up, you are treating latitude as a factor. But I guess I would think of it as like it is numeric, because 31 is closer to 32 than is 47. 45 is close to 47. So like it's not a linear relationship. If it's something, maybe nonlinear, we have some breaks like 31, 33, 35 are all kind of the same. And then probably there's some kind of oceanographic break between 35 and 37 that causes that like seasonal thing.
Yep.
So thoughts on that? Could you do that? Could you treat latitude as a numeric?
In this framework, yes, you could. You could include the way to do that in these GAMS were to be to, you could have your smooth, go back to location. So let me find one of these model calls. Yep. So the way that I think you could do that would be to get rid of, so you could get rid of your the random effects here, and you could include a two-dimensional spline or two-dimensional smooth over time and latitude as a numeric variable. Here, latitude is already a factor because I made it that, but you could include it in this thing here as just a 2D smooth that would let the effect let you model the interaction between time and location. So that's one way. Another way would be to just fit a full-blown spatial model to that, and I can talk more about that on Thursday. But Eli is right, where like if we fit these kinds of models, one of the downsides is that they are ignoring the spatial autocorrelation that could be present. And so if you looked at the residuals here and looked at the pairs of residuals across locations, you'd expect those residuals from location 31 and 33 to be more similar than between 31 and 47. And so I think this approach is just treating them all as independent, which obviously they're not. Any other questions? All right. Well, maybe why don't we come back at 1:45? Does that work? Break, and we can dive in the lab then. Right.